Hi, my name is Jarek Van, and this is my Physics 2 lab reports on circuits. So this is the introduction. The purpose today is we're going to investigate and predict the behavior of circuits containing resistors in series and parallel, and we will be displaying that with a FET simulator. And we'll be investigating the behavior of ohmic resistors and capacitors as well, and we want to be able to predict and measure the currents within our circuit, and of course we want to measure the actual values of conventional current and potential differences within the circuits. And within the series circuits that we constructed, we have of course our two batteries, we have our ammeter, our two resistors of different magnitudes of resistance, and another ammeter on our circuits. And of course, at each node, there will be differences in electric potential. Between the batteries, we have a positive 3, and then we have negative 0.96 between the beginning and end of the first resistor, and negative 2.04 volts of a difference in electric potential from our E and F point, which is the beginning and end of our second resistor. Of course, the sum of the electric potential is 0 volts, showing our conservation, our loop rule. And additionally, we predicted the current to be 0.02 amperes using equations we've learned in the course, and the FET simulation calculated the same value as shown in our ammeters. Next, of course, we have our introductory measurements. We have principles of energy conservation, loop rule, and current conservation, and our steady state. So energy conservation and our loop rule. Energy is conserved within our circuits. The current conservation, we have current going in is equal to current going out. And of course, we have our steady state, which states that we have a non-accelerating flow of the electrons through our currents. And then we have graphical analysis, of course, with a graph given to us in our lab intro. Of course, we begin at the beginning of our circuit. We have our change in potential between the two batteries. You can see the two bars of equal magnitude representing the two batteries, adding up to 3 volts. No change in electric potential from B to C. And then we have a dip with magnitude negative 0.96 volts from C to D, our first resistor of 47 ohms. And then, of course, we go delta V equals 0 volts from T to E. And then we have another dip all the way down to 0 volts of negative 2.04 volts, resulting from our 100 ohm second resistor from E to F, of course. And of course, as always, initial current is equal to final current. That is our graphical analysis. And now we tested a different type of circuit, the ammeter in parallel. This increased our current from 0.02 amperes to 0.06 amperes. This results in our ammeter being in parallel with the second resistor. So as we trace the flow of current, some will go into the resistor and some will go out of the resistor. And when electric current goes into the resistor, it decreases the current. That is the whole trademark characteristic of resistors. It decreases the current going in, but since some of the current is able to exit and enter the ammeter and conserve the current that went in and out of the ammeter, we have a higher current. This is the RC circuits that was built by my group and I in our lab session. As you can see, 2 batteries, of course. And then we have our continued RC circuits, which we built with a 9-volt battery, 30 ohm resistor, which in the form of a light bulb, and a 0.2 Faraday capacitor. And then we have our voltage on RC circuits continued. Again, same setup. different scenario, etc., etc. And then we have our conclusion. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it have affected the circuits you hooked it up to? A real ammeter is not able to perfectly conserve the charge going into it and out of it once you measure the charge. So the measure of current, sorry, not charge, current. The measure of the current is going to be less than the actual simulated. That's the ideal ammeter. Charge is conserved fully and wholly throughout the whole circuit. But of course, a real ammeter, as most things in real life, charge is not conserved. Energy is often not conserved because of external forces, etc. And then for our second discussion question, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Our ideal model would predict the capacitor to reach full charge quite quickly, especially considering there is no resistor. It would not be as ideal and as quick as it would if we simulated in our PhET simulation, but as we mentioned earlier, no conservation. But still, it would be significantly quicker, and it would have, this prediction would happen in real life. So thank you guys for watching. This is my Lab 4 presentation.